All right, so this is the third page of our second review packet, and we're looking at question number 11. This would be a non-calculator AP problem. A function is f is continuous on the closed interval -3 to 3, such that f of -3 is 4, f of 3 is 1. So we've got -3, 4, and 3, 1. The functions f prime and f double prime have the properties in the given table below. I think we saw this problem earlier in the year in a big packet I gave you, but I don't think I gave you the full question. Okay, so or maybe I did. I don't remember. All right, so part A. What are the x coordinates of all the absolute maximum and minimum points of f on the interval -3 to 3? All right, so remember this is a continuous function, and f prime tells us whether f is going up or down. So this graph, I'm just going to sketch. Well, part C is sketch the graph. I'm just going to do a rough sketch here. We know at -3, we're at 4. And at +3, we're at 1. So remember, candidates for absolute extrema are, I just make a table here, are the endpoints, so -3 and 3. And then any places where we have relative extrema, so relative max or min. So this graph for f, it increases until we hit -1. So it increases for a while and then decreases, flattens out, and then decreases again. So increases for a while. The reason f prime is non-existent at -1 is because there must be a sharp turn. So it decreases for a while, and then at 1, we have like sort of a horizontal tangent like that, and then it decreases some more. So it's something like this. That means that anywhere f prime changes signs, there's a potential absolute max or min. So there's a relative extrema here at -1. And we do know the values for these two graphs. Based on my sketch of the graph, I know that at -1, this has to be something greater than 4 because f of x increases from x equals -3 to x equals -1, and then decreases from, there's probably a more efficient way to say this, from x equals -1 to x equals 3. I'm sure there's a shorter way to explain all of this. So if that's the case, it means that there's an absolute max. It just wants the x value. So at x equals -1. We don't have enough information to find the y value. That's why they just want the x coordinates. And then what about the absolute minimum? Well, I know where the graph ends. It ends at 1, and it decreased from the point at x equals -1 to the point at x equals 3. But all the points prior to 3 were higher because we were decreasing that whole time to get down there. So there's an absolute min at x equals 3. Justify your answer is just done with the extreme value theorem, really. I don't think we have to say by extreme value theorem, but the only candidates are the endpoints and the relative extrema, and f prime only changes signs at -1. It does not change signs at 1. So there's no potential for a relative max or min at x equals 1. So that's it. All right, part B. What are the x coordinates of all points of inflection on the interval -3 to 3? So points of inflection happen when concavity changes. And remember, that happens where f double prime changes signs. So it does not change signs on either side of x equals -1. See how it's concave up and then still concave up? But it does change concavity here. We go from positive to negative. So for part B, there's a point of inflection at x equals 1. And that's because f double prime of x changes signs. And I think this is like, I don't know if this is redundant, but if f double prime is changing signs, it definitely hits 0 at x equals 1. But I'm just going to throw it in there. And f double prime of 1 equals 0. Or you could say is undefined if that were the case there, because those two things kind of need to happen. The equal to 0 or equal to undefined makes it a possible inflection point, and the changing signs is what changes this to an actual point of inflection. Okay, part C, sketch the graph. So I already kind of did that, but include units on your axes and all that stuff. So we do know, here's x, here's f of x. We do have two specific points we can plot. So at -3, we're at 1, 2, 3, 4. And at 1, 2, 3, we're at 1. And we know that at x equals -1, there's some sort of a point, or there's a what do I want to say? A point where the graph is not differentiable, so a cusp, because it's continuous. And then as I sketch this down, I have to make sure I have like a horizontal tangent somewhere at 1, which I do because we're switching from concave up to concave down. You don't want to put arrows on either end because we don't have that information. So this is my graph. All right, let's do the next problem. Number 12. Get this all set up so I can write on it. All right, so number 12, let h be a function defined for all x not equal to 0 such that h of 4 equals -3. So here's an ordered pair, 4, -3. And the derivative of h is given by this h prime. This has x squared minus 2 over x for all x not equal to 0. And this is no calculator. So part A, so we don't know h, but we do know h prime. Find all values of x for which the graph of h has a horizontal tangent and determine whether h has a local max, local min, or neither. Justify. All right, so first let's find the horizontal tangent. Sometimes I justify first to get my brain flowing here. So h has a relative extrema. Has a horizontal tangent when h prime equals 0. So let's set that up. H prime equals 0 when x squared minus 2 equals 0. The x would get multiplied away, and we already know x can't equal 0. So that's when x squared equals 2, and that would be when x equals plus or minus radical 2. So that's part 1. And then at each of those values, is it a relative max, min, or what? So now we need to do the first derivative test to figure that out. So we're going to look at what's happening with h prime. I almost wrote f. And negative radical 2 would be here. Radical 2 would be here. We're plugging into the h prime equation, which is x squared minus 2 over x. So say I plug in something like -3. That's going to give me 9 minus 2 over -3. That's negative overall. If I plug in 0 between these two, I get negative. Oh, I can't plug in 0. Sorry. I should remember to put an undefined value in there so that we can't use that. So sorry, I can't do 0 because I would get -2 over 0. That's no good. So let me test like -1. So -1 squared is 1 minus 2 over -1. That's positive. And then I can test 1. So that's 1 minus 2 over 1. That's negative. And like 3 would be 9 minus 2 over 3. That's positive. So remember, h does not exist at 0. They've told us that. So even though we change signs at 0, that's not a relative extrema. It's probably just a place where h is unbounded. But h goes from decreasing to increasing, decreasing to increasing. So at x equals plus and minus radical 2, those are both, local minimums, because I I keep saying F instead of H. That would matter, by the way. So because H prime of X changes, it's not just changes signs, it specifically changes from negative to positive at both values. Okay, so they're both relative minimums. Part B. On what intervals, if any, is the graph of H concave up? So again, I like to just think about like, well, what is concave up normally? So H is concave up when H double prime of X is greater than 0. Now, we don't have H double prime of X, but what is, how does that relate to, well, I guess we could find H double prime of X. But that could also relate to when is H prime increasing. Although this function is kind of like when is it increasing? This is not something I can just easily sketch, I don't think. So maybe I should go ahead and find H double prime. So let's see. So H double prime is equal to, we can either use quotient rule or we can just divide here. So actually, let me write down what H prime is equal to. Sorry, I'm all over the place here. So let's simplify H prime of X. So it's X squared over X, which is X, minus 2 over X. So that's just me dividing the original two terms by X. And then H prime, double prime, so that I don't have to do quotient rule, will just be 1. And then, so this is minus 2x to the negative 1. So this would be plus 2 over, taking a derivative, right? So 2 over x squared. Sorry, I almost started integrating here. And we can, I like to get this into one denominator so that it's easier to set equal to 0 or not equal to 0, whatever. All right, so we have this. And when is H concave up? It would be when this is positive. And really, this is always positive, except remember, we can't plug in 0 into this. So H double prime of X is greater than 0 for all X not equal to 0. Or you could say negative infinity to 0, 0 to infinity. But I think I'm just going to answer it like this. And I know that because these x squareds are positive and we're just adding 2. Write an equation for the line tangent to the graph of H at x equals 4. All right, so that should be easy. We need a point and a slope. The point is when x equals 4. We were given that point at the beginning. Y is negative 3. And the slope is to evaluate H prime of 4. So H prime was x squared minus 2 over x. So 14 over 4 or 7 over 2. Now write the equation just in point slope form. Y plus 3 equals 7 over 2 times x minus 4. Hopefully that's like a free point or two when we see this on the AP test, where you're going to have to write a tangent line equation. Does the line tangent to the graph of H at x equals 4 lie above or below the graph of H for x greater than 4, and why? So the tangent line. So they're asking me about this. Is the line below the graph? Like here's the point of tangency at x equals 4. Is the line below the graph over here? Or is the line above the graph like this? Well, what's the difference? Concave up versus concave down. So remember, we said that H is concave up for all x not equal to 0. We just said that in part B. So that means that the tangent line is below H of x for all x greater than 4. They're equal at x equals 4, but then for any x, really, it's sitting below. All right, let's do one more. Oh, no, sorry. We'll try to get 2 more in. All right, so take a look at 13. Get myself all set up here. Okay, so for number 13, consider the curve defined by x squared plus xy plus y squared equals 20. That says 27. Sorry, this is really strangely pasted. Write an expression for the slope of the curve at any point xy. So in other words, they're asking me to find dy dx. And because I can't easily solve this equation for y, get y by itself, I need to differentiate with respect to x on both sides. Or in other words, this is implicit differentiation. All right, so the derivative of x squared is 2x. The derivative of xy, remember this needs a little product rule. So first times derivative of the second plus second times derivative of the first. And then the derivative of y squared is 2y. And we have to chain rule because we're taking the derivative with respect to x, and this is a variable that's not x. On the right side of the equation, the derivative of any constant is 0. So I need to factor the dy dx out of the two terms that have it. I need to move anything that doesn't have a dy dx on it to the other side. So minus 2x minus y. And then finally, I can solve for dy dx. So negative 2x minus y over x plus 2y. It kind of seems like something should simplify there, but it doesn't. If you factor a negative out, you do not get the same expression top and bottom, so nothing reduces. And that's it. That's all I had to do for the first part. Okay, for part B, determine whether the lines tangent to the curve at the x-intercepts of the curve are parallel. Show the analysis that leads to your conclusion. So first, let's find the x-intercepts. X-intercepts are x values where y is 0. So on the original curve, we should be plugging in 0 for y. X squared plus x times 0 plus 0 squared equals 27. So really, it's just 1 is x squared equal to 27. So the x-intercepts are plus or minus radical 27, or 3 radical 3. So I found the x-intercepts. Determine whether the lines tangent are parallel. So we need to evaluate our dy dx at each of those values. And remember, they're x-intercepts. So negative 3 radical 3 for x and 0 for y. So plug into that dy dx we just found. That's negative 2 times negative 3 radical 3 minus 0 over negative 3 radical 3 plus 0. That's positive. Well, so the zeros are gone. This cancels out. So that's just negative 2. And then let's see what the other slope is, if it's the same or not. So dy dx, evaluated at positive 3 radical 3, 0. It's negative 2 times 3 radical 3 minus 0 over 3 radical 3 plus 0. That also comes out to negative 2. So yes, they are parallel. Okay, what about part C? Find the points on the curve where the lines tangent to the curve are vertical. So I'm going to do a little justification first. I need dy dx to equal undefined, and that happens when the denominator is equal to 0. So 2y would equal negative x. And let's see. I can either solve this for y, where x is negative, or where y equals negative x over 2, but then I have to plug back into here, and that's going to give me fractions that I don't really want to deal with. There's no rule that says you have to find x first, so I think if I leave this, if I solve this for x, like this, I can then plug in negative 2y for all of the x values, and then just find y first, and then go back and figure out what x is. So x squared, so negative 2y squared plus x times y, negative 2y times y, plus y squared is supposed to equal 27. So this is 4y squared minus 2y squared plus y squared equals 27. That's 2. So 3y squared equals 27. Oh, this is coming out nicely. Y squared is 9. Y is plus or minus 3. What do I do about x? Remember back here, x is equal to negative 2y. So x is equal to, well, it kind of matters which is which, so let's pair these together. So the 2 points, they want me to find the points, right? So there are vertical tangents at, so when y is 3, x is negative 6. And when y is negative 3, x is positive 6. So be careful. You can't just say plus or minus 6 and plus or minus 3. You have to get the correct combination. All right, I think there was one more on this page, and I've got time to do it. All right. So oil flows into a tank. This feels like related rates. The rate, or maybe it's Riemann sums here. Oil flows into a tank. The rate in gallons per hour is given by a differentiable function r at time t. So sometimes I like to label this just so I remember. Is there some time between 0 and 15 such that r prime of t equals 1/3? Justify your answer. So this is asking you if the instantaneous rate of change matches any sort of average rate of change. Is there an average rate of change that comes out to 1/3? Go with the endpoints of the interval here. So let's just check this for the first part. Is r of 15 minus r of 0 over 15 minus 0, does this come out to 1/3? So 10 minus 5 over 15, 5 over 15 is 1/3. Yes. So what do I have to do to say this? Like, yes, the average rate of change is 1/3, and that means there has to be a time here. It's because of mean value theorem. So what we know about this is r is continuous because it's differentiable and differentiable on this interval, 0 to 15. I guess it's the open interval, sorry. And so by mean value theorem, there must be at least one t such that r prime of t equals 1/3, because that equals r of 15 minus r of 0 over 15 minus 0. All right. Approximate this integral using a midpoint Riemann sum with 2 equal subintervals. Oh, that's weird. Include units in your answer. 2 equal subintervals. So delta x, we're going from 0 to 12, not 0 to 15. So delta x is 12 minus 0 over 2. So delta x of 6. So 0 to 6, 6 to 12. The midpoint you're going to use is the 3 and the 9. And it's a midpoint Riemann sum. So the integral from 0 to 12 of r of t dt is about equal to, they're both rectangles are going to have a width of 6. And we're going to use 8.5 plus 10.1. You can just leave your answer like this. This is free response. Of course, we could simplify, right? Shouldn't be too bad to simplify, but we could leave our answer like this and then include units. So if you're getting confused on units, go ahead and write them next to each other like this. You just multiplied r of t times dt. R of t is gallons per hour, and you just multiplied it by the width, which is dt, which is hours. That's going to leave you with gallons. It doesn't say to interpret, but this would be what is oil doing? It's flowing into a tank. This would be the amount of oil that the tank gains, I guess, or whatever, that flows into the tank from 0 to 12 hours. Part C, approximate the average rate that the oil flows into the tank during the first 12 hours. Include units. Average rate is R average. It doesn't say average rate of change. It's just R is a rate. So find the average. That's 1 over 12 minus 0 times the integral 0 to 12 of R of t dt. And we're approximating it. So we just found this integral here. So we just need to divide it by 12. It's this answer divided by 12. And again, I'm really not going to simplify this. I don't need to, but I could say, here's 1/2, divide each of those by 2, and then the math would be much easier, I'm sure. Include units in your answer. We just took a total number of gallons and we divided it by a change in time. So we're back to gallons per hour. Here you're finding the R of t times dt. You're finding that like sum basically. And then here you're still finding an average value for R, which is measured in gallons per hour. All right, was that the last one on this page? Yes, I'm going to stop this video here, and then we'll have a video for the next page.